The cerebellum, the little brain, this guy back here. I have talked about this before in a video. It was back during COVID, back when I had my last haircut, I think. Back in my back garden because we were in lockdown. Now that I'm in the anatomy labs, we should talk about the cerebellum again, carefully. And we can talk about, we can point at things, right? I got the 3D thing. We can talk about the lobes and the fissures and the things and the peduncles and the blood supply, all the things. So that's what we'll do. So the cerebellum is here. This is the cerebrum. It's huge. The cerebellum is back here. And we have left and right sides. So it's much, much smaller than the cerebrum. So it's inferior to the cerebrum. Here is the brainstem, the medulla, the pons, and the midbrain up there. So it's posterior to the brainstem. And if we were talking about cranial fossae, the bony spaces inside the cranial cavity, it's in the posterior cranial fossa. So that's where it lies. Fun fact, best estimate these days is that the central nervous system has 86 billion neurons, and the cerebellum maybe has 69 billion neurons. So the cerebellum maybe has 80% of all of the neurons of the brain, which is an astounding fact. And the reason why it has so many neurons is because its role is in movement. And movement, while it seems very straightforward, is incredibly complicated to manage. Think about all the dexterous things that you can do without thinking about it. It's because your cerebellum is doing the thinking for you. It's the cerebral cortex that decides to make a movement. So if your upper motor neurons run from your motor cortex down the spinal cord and innervate lower motor neurons that then run out to your muscles, how does the cerebellum get involved with that? Well, when you want to initiate a movement, information goes from the cerebral cortex to the cerebellum through circuits in the cerebellum, and then back to the cortex and then down the upper motor neurons. That is, the cerebellum is adding to the intended movement. The cerebellum is also looking at what was intended and comparing it to what actually happened, and can make changes to that, and that's how you learn new movements. If you've learned the golf swing, it's incredibly complex. If you've learned how to swim well, it's incredibly complex. You learn each part of each movement, and then you practice that, thinking about it, and with practice, each part of the movement as a whole gets better, and then the movement as a whole gets better over time. To put it in a simpler way, you probably learned how to ride a bike. It took you a while to learn how to ride a bike. The cerebellum is taking all that sensory input about balance and movement and position and how your legs and your upper body and everything else is moving and how you're turning the handlebars. Taking all that sensory input, manipulating the motor output, you learn how to ride a bike. And once you learn how to ride a bike, you never forget because it's in here. And the same with any complicated movement like typing on a keyboard, signing your name, all that sort of, that's the cerebellum. It does have other functions, but the motor functions are the ones we know about best. That's enough about function. We'll come back at the end to what happens if it gets injured. But let's look at the gross anatomy, because that's what we're really interested in. Okay, then if I take this cerebellum off, something we see on the cerebrum is we see these grooves and these folds, the gyri and the sulci, right? And they look like that. And then when you look at the cerebellum, you see the same features, but they're much finer. So these folds are the folia, and there are much finer folds because then you can create more surface area, and the grey matter is in the outer part of the cerebellum. The white matter is in the inner part. So the grey matter is where you have neuron cell bodies. It's grey because you don't have myelin there. You have lots of connections instead. This is where the connections and a lot of the circuitry happens. So the grey matter is where you've got neuron cell bodies and connections. The white matter then is more central. That's where the axons are running out or running into the cerebellum. And those axons are myelinated, hence why that is white matter. So The tighter the folds, the more grey matter you can have, the more neuron cell bodies you can get in there, the more connections you can get in there, the more complexity. That's why it's so highly folded, and those are the folia. With respect to the white matter, so here we can see the white matter inside the cerebellum. Another word you might come across when people are talking about the cerebellum is the arbor vitae. Arbor, tree, vitae, life, the tree of life. And that's this branching pattern that we see within the cerebellum, looking like a tree of life. Arbor vitae. We can see left and right hemispheres. If we rotate around the cerebellum, you can see there's a notch posteriorly and there's a notch anteriorly. That's the anterior and posterior notch of the cerebellum, but shapely features. And in amongst these folia, we can see kind of deeper grooves, which are the fissures. And you can divide up the cerebellum at those fissures to create lobules. We have lobes, we have lobules. Yeah, we'll come to that. And then if we look on the anterior surface, we've got that sort of a shape. We'll describe all of that in detail as well. And in the middle, you've got something that looks like a worm, right? Looks like a worm. Definitely a worm. Totally looks like a worm. That's the vermis. Vermis means worm. You might have also encountered vermis in vermiform appendix, the appendage that hangs off the cecum that is vermiform, worm-shaped, because it also looks like a worm. Right, so the vermis is the central part of the cerebellum, and then we have the left and right hemispheres on either side. So, if we have our cerebellum, that's the superior surface there, up against the cerebrum. This is the posterior surface and the inferior surface up against the bone, right? If I spin this around, then that's the anterior surface and the brainstem is here. If this is the vermis in the midline on this superior surface of the cerebellum that's up against the cerebrum, kind of, can you see that this groove here is deeper? This is the primary fissure. So it's a little bit deeper than the others. Now, if this was a real cerebellum, I would be able to move this and show you how it is a deeper groove. But that is one of the fissures. That's the primary fissure. And what that does is that shows you where the anterior lobe is. The anterior lobe is anterior to the primary fissure. And everything else around here is the posterior lobe. So most of this is the posterior lobe. This little bit here is the anterior lobe. The other fissure of note is the horizontal fissure. So if I spin this around and we look at the anterior part of the cerebellum, we can see quite an obvious fissure here. And it's running more horizontally than the other fissures. This is the horizontal fissure. Now, as we follow this horizontal fissure around, so the horizontal fissure runs around here, and it's just one of the notable fissures, really, which is likely to come up. And see how it runs around to this posterior groove here. Now, if we look at the anterior cerebellum, there's a lot of lumpy bits. We'll work our way through the lumpy bits. But this is the most important lumpy bit. So we also have the flocculonodular lobe. So anterior lobe, posterior lobe, flocculonodular lobe. Now this is the flocculus here, this little lump. And the nodule is in here. And they are continuous. So this whole section here is the flocculonodular lobe. So that's the third lobe. So there are 3 lobes on either side, and there are 2 hemispheres. Now there's a fissure, so that horizontal fissure continues, and that fissure separates the flocculus from the posterior lobe, and that is the posterolateral fissure. Now, each hemisphere can also be broken up into 9 lobules. I think that's a bit much. It can also be broken up into functional units. So the 9 lobules are broken up by the fissures into anatomical subunits. I might label all those now, but I'm not going to stand here and talk my way through all of those lobules. Like I say, it's a bit much. I'm still going quite deep, but I'm focusing on the stuff that often comes up. So vermis, anterior lobe, posterior lobe, flocculonodular lobe in there. Now in here, we have also got some interesting lumps. Now the vermis, classically, is part of the lobes, but it often gets described separately. And it also can get divided up into 9 segments. But the fun ones in terms of language, you'll see where I'm going with this in a minute. So this is the anterior part of the cerebellum, the bit that's up against the brainstem, right? So we're looking at the vermis here in the midline, and this central lump is the central lobule of the vermis, which is nice. And then we've got a little sticky outy bit here. It's kind of sticking out like a tongue, right? Right? That is the lingula, which means tongue. And then down here, can you see this bit? Looks just like the uvula in your mouth that hangs down from the soft palate, right? Just like it. That's called the uvula. So that's the uvula. So we've got central lobule, lingula, uvula. So we're thinking about the oral cavity when we're naming these structures. And then these lumps down here are called the tonsils. So if you've heard of the cerebellar tonsils, that's what they are. That's why they're called the cerebellar tonsils. Now these are actually parts of the posterior lobe here. Now why are we interested in the cerebellar tonsils? Dura mater is the tough connective tissues, one of the meninges, that holds everything in place, right? So if in there, that's where the cerebellum sits, like that, the cerebellum is then separated from the cerebrum by the dura mater. The dura mater between the cerebellum and the cerebrum is the tentorium cerebelli. Tentorium, it's like a tent. It's a tent of dura mater over the cerebellum that separates the cerebellum from the cerebrum. But there's a gap, right? There's got to be a gap because the brainstem has to pass through to get to the cerebrum. So there's a tentorial hiatus, so a gap anterior to the tentorium. So that tentorial hiatus is where the midbrain passes through. Great. Now, if somebody has a supratentorial mass, that means they have a mass superior to the tentorium. So the mass is where the cerebrum is, let's say. That mass could be a tumour, could be an abscess, could be a bleed, a supratentorial mass. Now, because this is made of bone, it's not stretchy. So there's a limited amount of space inside here. So if there's a supratentorial mass in here, that mass is taking up space. So it will be pushing the very soft brain out of the way. There's only one direction, there's only one place for that supra soft brain to go, and it's down through that tentorial notch between the clevus, the bone here, and the tentorium cerebelli. Now, if something's getting pushed down through the supratentorial notch, it's now getting pushed into the posterior cranial fossa, the same place where we have the brainstem and the cerebellum. And if something pushes into where the brainstem and the cerebellum are, then the very soft brainstem and cerebellum are going to get pushed out of where they are. There's only one place for them to go, and that's out through foramen magnum, out through the hole in the base of the skull where the spinal cord goes out. And if that happens, the inferior most part of the cerebellum that gets pushed out through the foramen magnum is going to be the cerebellar tonsils. And that's called tonsillar herniation. That's what that means. It means the cerebellar tonsils are herniating out of the cranial cavity through foramen magnum. This is also called coning. This is very bad because this means that the brainstem at this point is being crushed by whatever's descending. It's getting crushed up against the bone. And in the brainstem, this is where you have your vital for life circuits. And if the brainstem is crushed and damaged, that will lead to death. So coning, herniation of the cerebellar tonsils is a very, very bad sign, and it's a sign that death is likely to follow soon. So that's what we mean by all those words, and that's where the tonsils bit comes from, okay? Peduncles. Ignore those holes in there, by the way. They're just for attaching this to the rest of the model, which doesn't want to stay together. So the peduncles, so a peduncle is a stalk, and all of that circuitry in the cerebellum needs some pretty chunky, high throughput connections to the rest of the central nervous system. So there are 3 peduncles on either side: superior, middle, and inferior cerebellar peduncles. That's nice, right? And of course, the cerebellum is posterior to the brainstem, so they are connecting to the midbrain, the pons, and the medulla oblongata. I don't think I really need to go into more detail in terms of connections because it rapidly gets really complicated. But both the fun thing and the very useful bit of information when you're trying to work out where everything is in the central nervous system and how it's all attached, because it's quite difficult because you can't just pull it apart like muscles and stuff. But there are 3 peduncles on either side then, so superior, middle, and inferior peduncles, and then you've got the cerebellum, and then you've got the brainstem. They leave a space in between themselves. So if I unplug the cerebellum, the space that's left, or the space that's made by those peduncles going out and around, the space there is the 4th ventricle, is what I'm trying to say. This is the 4th ventricle of the cerebrospinal fluid system. So if you're trying to work out where you are in transverse sections, you know, when you're trying to look at brain stuff and you're trying to figure out what's what, when you see the 4th ventricle, that's made by the peduncles of the cerebellum. So the cerebellum is posterior, and we can see actually that largely it's the pons that's anterior. And when you're looking at brainstem anatomy and cranial nerve nuclei and things like that, they often refer to their position relative to the 4th ventricle. And I don't know, it's just when you start to get this 3D stuff in your head, it all starts to make some sort of sense. But yeah, you've got 3 peduncles forming the walls of the 4th ventricle. The anterior wall of the 4th ventricle essentially is the brainstem, and the posterior wall of the 4th ventricle is the cerebellum, basically. So peduncles. So the peduncles then, yeah, they're carrying white matter. So they're white matter tracks carrying them to the cerebrum and thalamus and back and what have you. That might be it, except for blood supply, which is a quick one. There are 4 arteries that supply blood to the brain. There are 2 internal carotid arteries that are anterior, 2 vertebral arteries that are posterior. The cerebellum is in the posterior part of the head, so it receives blood from the posterior circulation. That is, you have your 2 vertebral arteries coming up here, and they join to make a single basilar artery that runs between the bone and the brainstem, and then ends as the posterior cerebral arteries, which runs to largely the posterior cerebrum. And along that route, you have 3 pairs of cerebellar arteries. Now, the trick here is that the brainstem is ascending, and it's also running from posterior to anterior, right? It's not going straight up. There's a bit of an angle to it. So the brainstem is running from inferior to superior, and it's running from posterior to anterior. The reason that's important is the 3 pairs of cerebellar arteries are the posterior inferior cerebellar artery, pica, the anterior inferior cerebellar artery, aica, maybe, and then the superior cerebellar arteries. So the posterior inferior cerebellar arteries tend to be branches of the vertebral arteries themselves. The anterior inferior cerebellar arteries are then branches of the basilar artery, and then the superior cerebellar arteries are branches of the basilar artery just before it ends as the two posterior cerebral arteries. Careful with the E's, yeah, cerebellar and cerebral. And I think on this model, you get a sense of, not just this model, but also where the arteries are. You get a sense of the regions supplied with blood by those different arteries. Venous drainage is to dural venous sinuses. Use your imagination. What is around? So the cerebellum is back here. Well, there we've got the transverse sinus. We've got the petrosal sinuses over here, and in the middle we've got the vein of Galen, or the great cerebral vein. Blood from the cerebellum is draining to those, essentially. Okay, so if the cerebellum is damaged, maybe by one of those arteries being occluded by a clot, by a thrombus, and part of the cerebellum becoming ischemic, what would happen? Well, anything movement related would be affected. Cerebellum movement, okay, so anything movement. So walking, problems with gait, you might see, so it's involved in, coordination of movements and balance and that sort of thing. So walking, you might see a wide gait, an unsteady gait, changes to gait. Ataxia is that uncoordinated voluntary movement thing. Nystagmus, flicking of the eyes, because this is a complicated movement. The movement of the eyes, again, cerebellum's involved in all of that. So nystagmus, that's when the room is spinning and your eyes are flicking from side to side. Dysarthria, difficulty speaking. Movement, right? Complicated movement. Difficulty coordinating. So difficulty speaking. Not like I am now. I mean, slurred speech, difficulty putting those words together. Anything movement, basically. And it can be kind of difficult to separate from vestibular syndromes because of the sensory input from the vestibular system also having effects on movement in the same sort of way. So cerebellum injured, movement, difficulty with coordinated movement. Dysdiadokinesia, was that right? So rapidly alternating movements. Any movement, problems with movement. Okay, that's the cerebellum. That's the gross anatomy of the cerebellum. Microscopic anatomy of the cerebellum is also very interesting. Anyway, I think I have covered what I think is useful at this stage, and you can certainly add to this. And in fact, humanity as a whole is still adding to this because we don't entirely understand the cerebellum, and it seems to have other wider cortical functions as well, but that's for the future. Okay, I hope that was helpful, useful. I'll see you, I won't see you next week. I'm going away for a few weeks. I'll see you in the future.